Okay, thank you, Dr. Jayas, for this introduction, and thank you all for being here today. It's a great pleasure to talk to you about one of the most exciting fields in high-energy astrophysics. And I'll try to convey to you some of the excitement in this field, the field of supernova remnants and neutron stars. So to start with, let's start our journey by going out on a cloudless night and looking up at the sky. And what you might see is something like this. If you're lucky, you see lots of stars, and you might notice that some of them are bluish in color. And then you go back and look up again the sky the next night. You might see the same thing. You go back another night, you see the same thing over and over. But one night, something unusual might happen. You suddenly see a bright star in the sky. And you might guess this is a new star that's born. But in fact, this is a dead star. It's a star that's exploded, and the explosion is called a supernova explosion. It's one of the most energetic explosions in the universe. So you wonder about the fate of our sun, and our sun, in fact, is not going to turn supernova. Our sun is going to follow this path here. So this is a plot which shows the evolution of stars as a function of their mass, with one being the mass of the sun. And as you see, the sun will end up eventually into what we call a white dwarf, and that will take about 5 billion years to happen. A white dwarf is a star that's small. It's about the size of the Earth. Now, stars more massive than the sun, about 10 times or more than the sun, will follow this path, and they will die in dramatic explosions called supernova explosions, and they will form exotic objects, neutron stars, which I'll be talking about today, or if they're very, very massive, they might turn into black holes. So let me first start with some definitions and the interesting questions to us humans on why we're studying these objects. So first, just to make things clear, a supernova is the result of the explosion or the death of a massive star, a star at least 10 times the mass of the sun. Now, these explosions are so energetic that in a matter of seconds, the explosion releases more energy than the sun releases in its entire 10 billion years of lifetime. Okay? This is how energetic they are. And when the explosion takes place, a very fast-moving blast wave moves out in space at millions of miles per hour. Imagine how fast that is. And then it shocks the interstellar medium to extreme high temperatures. And these objects shine in very high energies, X-rays, and even gamma rays, and I'll talk about that more later. Now, the remnant of the explosion is called the supernova remnant. These are the debris of the exploded star, and near the center, you're left with the corpse, the stellar corpse, which we call a neutron star, and in some cases, black hole. So these are the definitions, and you'll hear me saying these words over and over during this talk. But the main questions to us humans is, how relevant are these to our life? And as you already heard from Dr. Jayas, these are extremely important because without them, we wouldn't exist. And I'll show you that. And I'll show you why that's the case. The second question, I told you these are extremely energetic, so you might wonder, how harmful are these to us? And the third question is, okay, what have we learned from the past? These objects, at least neutron stars, have been discovered 40 years ago. So I'm going to give you a brief glimpse of the past, what we know now, the present, and we'll switch gears and talk a little bit about the future. So I'm a high-energy astrophysicist, so I thought I'd clarify what I mean by high-energy astrophysics. So as you all know, our eyes are sensitive to what we call the visible light. And you all know that the electromagnetic spectrum spans a wide range of frequencies or wavelengths, shown here, going from the low-frequency radio waves to microwave to infrared, visible, ultraviolet, X-rays, and gamma rays. By high-energy astrophysics, I mean X-ray and gamma-ray astronomy. And as you see from this opacity plot here, you see that the atmosphere is opaque to X-rays and gamma rays, luckily, because we don't want these radiation to hit us. So since the atmosphere is opaque, we cannot get X-rays from the cosmos unless we send satellites up in space. So we get our data from satellites, and the data come to our computers. We do not need to go to telescopes to do observing. We just can do it from home, from anywhere in the world. And that's one of the advantages of being a high-energy astrophysicist. You're not restricted by weather. Of course, it's very expensive to fly missions into space. And this is NASA's Chandra X-ray Observatory, which was launched by NASA in the summer of '99. This mission is still up in space. It's doing excellent science, and it is the most powerful X-ray telescope currently up in space. It's so powerful, it has a resolution of half arc second, which is comparable to the Hubble Space Telescope for optical astronomy. It's so powerful that if you were to have Chandra eyes, you can read a newspaper from a mile away. And a lot of the images I'll be showing in this talk are taken from this powerful telescope, CXO. So I told you that supernova are relevant to us, and that's because they make the elements, the heavy elements that are essential to life. All these elements are made actually during the lifetime of the star before it explodes. Now this sketch shows you the structure of a massive star before it dies. We know that hydrogen is the most abundant element in the universe. Stars are initially made up of hydrogen, but because their cores are extremely hot, the extreme temperatures cause hydrogen nuclei to fuse and form heavier elements such as helium. Then helium fuses and form heavier elements such as carbon and oxygen, and so on. So heavier and heavier elements are formed during these so-called nuclear reactions. Now these reactions are exothermic, which means they release heat. Heat exerts an external force, which actually balances the inward force caused by gravity. And that's why stars are in equilibrium, more or less, because the outward force due to the thermal pressure balances the inward force due to gravity. But at some point, when iron is formed in the core, this is going to stop because iron is the most stable element, and as a result, there's no more exothermic nuclear reactions possible. The only force that's in action is the gravitational force. As a result, the star is going to collapse. The collapse causes the temperatures in the center to rise and the pressures to rise. Electrons and protons fuse and form what we call neutron, thus the formation of a neutron star. Now the outer layers, so the neutron star will be basically the collapsed core of the star, and the outer layers will be expelled in space during the event called supernova explosion, and eventually forming the supernova remnant. And I'll just show you a very quick movie illustrating a supernova explosion, which happens in a matter of seconds, leaving to, in the center, a collapsed star called neutron star. And here you see the outer layers of the star, the supernova remnant, which can glow in X-rays for hundreds of thousands of years. So we've known supernova for a while now. In fact, all the supernova that happen in our galaxy were recorded historically by Chinese, European, Arab, and other astronomers. And here is a list of what we call the historical supernova. These are the ones recorded in our galaxy. So it started back in 185. Then there's supernova 1006, 1054, that's the year. 1572 or Tycho, 1604 or Kepler, and that's actually an image which is taken from Kepler's book, which is a drawing illustrating the evidence for a new supernova denoted by the letter N here. And this is called the Kepler supernova because it was discovered by Kepler in 1604. And then the youngest known supernova in our galaxy is called Cas A, which is believed to be associated with year 1680. It's interesting, though, that since then, no supernova has been recorded in our galaxy, and that's a big puzzle. So how relevant are they to us? I already showed you that all the heavy elements, or at least up to iron, are formed during the nuclear reactions when the star was still alive. And actually, heavier elements, elements heavier than iron, happen during the supernova explosion itself. So here is a composition of humans, just to show you the elements that are formed during supernovae. And now I'll show you some images taken with the Chandra X-ray Observatory of supernova remnants, the remnants of these explosions. And these are all the images of the same supernova remnant called Cas A. I told you this is the youngest supernova remnant in our galaxy. It's about 300 years old. And these are the images of the same remnant, but what we do in X-ray astronomy, we dissect the X-ray energy range into different sub-ranges so that we illustrate the emission from the heavy elements we're interested in. So this is Cas A highlighted in silicon, this is calcium, and this is iron. So these are all false color images, so we choose the colors we want, but it immediately shows you the heavy elements which are scattered in space after the explosion. So calcium, we know this is a very essential element for our well-being. And of course, the Milky Way or supernova remnants don't have milk in them, but they are surely calcium rich. And you might wonder how much calcium actually there is in a supernova remnant. Can you make a guess? That's a very wild guess. That's a very correct answer. A lot, more than you can imagine. In fact, if you make the calculation, the mass of calcium in a supernova remnant is over 1,000 times the mass of the Earth, which corresponds to 2 followed by 31 zeros glasses of milk. They are certainly calcium rich. Okay, they're not only calcium rich, they're also oxygen rich. It depends on the actually the mass of the star that exploded. This is an example of a supernova remnant that's very oxygen rich, and the name of the remnant just refers to the coordinates of the remnant in the sky. And this is my opinion, an amazing picture, the nicest pictures I've seen for supernova remnants, which is obtained by accumulating 6 days of data on the Chandra X-ray Observatory. It's colored by us astronomers, and the colors refer to the heavy elements. So oxygen here is shown in red, neon in orange, magnesium in green, silicon and sulfur in blue. Again, it illustrates how we can image the heavy elements from supernova explosions. Now, I've been talking about the debris of the explosion, but I told you also that you expect to see the stellar corpse, the neutron star. Well, if you stare long enough at this image, you will see that there's a point right here, close to the center of the remnant, surrounded by a purplish nebula. We believe that this is the stellar corpse of the explosion, and it's a neutron star or a fast-spinning pulsar, which I'll talk about next. So now I'll switch gears and I'll talk about these stellar corpses, neutron stars, which we believe are some of the most exotic stars in the universe. Why are they so exotic? Well, let me first start with a brief historical overview of how these objects came about. Back in 1934, 2 astronomers, Walter Baade and Fritz Zwicky, they published a paper in which they say, with all reserve, we advance the view that a supernova represents the transition of an ordinary star into a neutron star consisting mainly of neutrons. That was an amazing statement at the time because it was in 1934, just around the time neutrons themselves were discovered. So they predicted the existence of stars made of neutrons, which, as you know, these are the subatomic particles which make up most of the nuclei in the universe. Well, it took over 35 years for their statement to be confirmed by observers, and that came with Jocelyn Bell, who was born in 1943. She's an Irish woman who was a PhD student of Anthony Hewish, studying in Cambridge in the UK. And she was actually building a radio telescope to study something completely different, quasars, which are the centers of very far away galaxies, powered by supermassive black holes. So she was interested in something completely different, and she was just building a radio telescope. Okay? And while doing so, she discovered in her data, which at the time were all accumulating on sheets and sheets and sheets of papers, not on computers, she found there's a little scruff, or a periodic signal, that would come every night with a period of 1 1/3 of a second. It was very periodic, and it would come every night. So that bothered her for a while, and when she talked to her advisor, they wondered if it is a sign of extraterrestrial intelligence, or which they dubbed as the little green man. However, they knew shortly after that it cannot be extraterrestrial intelligence. They found shortly after another pulsating star coming from a different region of the sky with a period of 1 1/2 of a second. So it's a different period. And shortly after, they published their paper in Nature, basically saying these are pulsating stars or pulsars. So pulsars is another name for neutron stars because they emit pulses of light. And that got Anthony Hewish the Nobel Prize in 1974 for this discovery. So let me tell you a little bit about these extreme objects and what we've learned in the past 40 years. They've been discovered exactly 40 years ago. They're about 10 kilometers in size, so they're about the size of Winnipeg. However, they're very massive. They're as massive as our sun. So just imagine squeezing the sun into the size of a city like Winnipeg. You get a neutron star. This is how dense these objects are. They're just like a giant atomic nucleus. They spin very fast because of conservation of angular momentum, and you might have heard of angular momentum. It's a quantity that's conserved, and just like a figure skater who's spinning, as she brings her arms inward, she's going to spin faster. Same thing for stars. As they get more and more compact, they're going to spin faster. Except in this case, the star is shrinking from million kilometers to 10 kilometers. That's a factor of 100,000, which means the period is going to, or the frequency is going to increase by a factor of 100,000 squared. Okay? So this is how fast they are. And also similarly, because of conservation of magnetic flux, Br squared, this is another quantity that's conserved. The radius shrinks by a factor of 100,000. The magnetic field is going to increase by a factor of 100,000 squared as well. So these are extremely strong magnets. We believe they are the strongest magnets in the universe. They're also very, very hot, unlike Winnipeg. They're extremely hot. They're millions of degrees Kelvin. And because of that, they shine in high energy X-rays and gamma rays. Some are detected as pulsars. So here I'm going to just explain to you why they are pulsars. This sketch illustrates the model for pulsars. It's like a lighthouse. So you have like a magnet which is rotating around this axis, the axis of rotation, and it has a magnetic axis which is misaligned along this direction. Now as these objects spin, they emit high energy particles, which we call it like a pulsar wind, along the magnetic axis. So I'm going to try to dance the pulsar dance here. So you imagine I am the pulsar. I'm going to rotate around my symmetry axis, but I also have a magnet. I'm magnetic, and I have the pulses being emitted along my magnetic axis, along my arms in this case. Okay? So you are the observer. You're the telescope. You're looking at me, the pulsar, and you're going to see. You're going to tell me what you're going to see as I'm rotating. Okay? So every time I make a rotation, if my arm intersects your line of sight, you're going to see a pulse, right? For every rotation, you're going to get a pulse, okay? And that's how pulsars work. Now, if your line of sight doesn't intersect my arms or the beams, you're not going to see me as a pulsar, okay? So that's why I say some are detected as pulsars. And also some power nebula. These are high energy cloud-like objects around these objects, and the most famous one is the Crab Nebula, which made its footprints in every single astronomy textbook. So this is the most famous nebula, which is powered by a very fast spinning pulsar, a pulsar spinning 30 times a second, and which was discovered 40 years ago. So just for fun, I thought I'll let you listen to some pulsar sounds. And these were recorded by some of the most powerful radio telescopes. And that gives you a feeling of how fast these pulsars are. Now, pulsars spin many times a second. Typically, they have periods of milliseconds. This one has a period of 0.7 seconds, so I hope you can hear that. Oops, sorry. Come on. It worked yesterday. Okay, let me try the crab pulsar.
Is that your sound output?
What's that? Oh, that's my
speaker output.
Okay.
What's your speaker output? Is that speaker output?
I'm not sure. I didn't need to.
I know.
Oh, that's too bad. Well, it doesn't matter. It's really cool. I'll show you probably after my talk during the break. If you're interested, you can approach me and I'll let you listen to this. But it's fascinating. Anyways, there's also, I have a movie which I hope works, illustrating also how pulsar winds are extremely dynamic. So I told you these pulsars spin very fast. As they spin, they spit out a highly relativistic wind, which we call a pulsar wind. And this wind interacts with the surrounding and energizes the surrounding. And now, thanks to very powerful telescopes like the Chandra X-ray telescope and the Hubble Space Telescope, we can actually image these winds and see what happens very, very close to the pulsar, something that was not possible a decade ago. So here I'll play the movie. And these images are with very similar resolution. This is the pulsar, which is spinning 30 times a second, spitting out a wind, which is visible here. And these images are taken on a few weeks to months time scale. So actually, by watching the evolution of these images, you can determine the velocity of these structures. And we found that it's very close. It's about 1/3 the speed of light. So these are highly relativistic. And thanks to Chandra and Hubble Space Telescope, we can now zoom on pulsar winds and understand how they interact with the surrounding medium. So now I'll move to magnetars, which is the more extreme side of neutron stars. And just to give you an idea about how magnetic these are, their magnetic field is 1,000 million times the magnetic field of the Earth. They are definitely the strongest magnets in the universe. Here I have a small movie illustrating what magnetars do. These were discovered in X-rays and gamma rays. They're very high energy objects. They're relatively slow in comparison to typical pulsars like the crab. In fact, they spin about once every 10 seconds. And the reason they're relatively slow is because of their high magnetic fields. We believe that the high magnetic field acts like a brake on the star. So it breaks it, which means it slows it down quickly in a short time. So they only live about 10,000 years, unlike other pulsars which can live for millions of years. And I'll show you here a movie. So this is the pulsar threaded by the magnetic field lines, extremely strong magnetic field. And as the pulsar rotates, in fact, it occasionally emits these bursts of light, which are the result of something similar to a starquake. The magnetic field is so strong that it causes a lot of stress on the surface. It cracks the surface, if you wish. And as the magnetic field is rearranging its configuration on the star, it releases a lot of energy, which we call a burst. And that's how these objects were discovered. They burst in X-rays and gamma rays. And these bursts are so energetic that a burst can emit in 1 second more than the sun emits in thousands of years. So that's probably what you care about. How harmful are they? Well, you certainly do not want to be very close to one of those. If you don't get killed by the X-ray and gamma ray radiation, you're going to be certainly distorted by their lethal magnetic fields. And also, if a magnetar is located halfway to the moon, it would wipe out the data from every single credit card on Earth. Well, luckily, we think we're safe, at least on millions of years timescale, because these objects are very, very far away, at least thousands of light years away. So we believe we're safe. And this slide just shows you the Nobel Prize winners in this field, just to illustrate how much work, how many breakthroughs have been done in this field. So these gentlemen won the Nobel Prize for their work on either neutron stars or X-ray astronomy. And I added here Jocelyn Bell in parentheses because, in fact, she did not win the Nobel Prize, even though she deserved it. But she's the one who discovered pulsars. And Anthony, who is her advisor, got the Nobel Prize for that. Okay, so now to switch gears, and I just want to give you a flavor of the future, especially for the young generation sitting here, possibly the future generation of astronomers, I hope. Some of you will go into astronomy. I'll just give you a brief glimpse of what the future is hiding. At least in my field, I have some burning questions that I'd like to see answered, and I believe they will be answered in the next decade or two. First, we'll need to find all the magnetars, these extremely magnetic stars in our galaxy. What I haven't told you is that we only know of a dozen, just 12, magnetars in our galaxy. That's a very small number. We know of over 2,000, roughly 2,000 pulsars, other regular pulsars in our galaxy. There's a huge gap. Why do we only know of so few magnetars? That could be related to the fact that they have a very short lifetime. I told you the magnetic field basically kills them very quickly. But there are other reasons for that. Magnetars have been discovered by accident. So if you don't happen to point your telescope to the right place in the sky at the right time, you might be missing the burst from these objects. You want to detect the burst from these objects to find them. Also, some magnetars actually disguise themselves in other forms. And in fact, just very recently, we discovered such a pulsar which has been behaving for the past 6 years as a regular pulsar, but just recently it behaved like a magnetar. So they could be like a schizophrenic pulsars who have double personality. We need to find all the missing pulsars in supernova remnants. There's about 300 supernova remnants in our galaxy, but only a few dozens pulsars inside those supernova remnants. We know we're missing a lot, but we also know that's because of the restrictions we have from technology. We know that with the advancement of instrumentation, with the advance of computational techniques, and with harder work, of course, searching for them, we're going to find all the missing pulsars in supernova. We're going to find all the missing young supernova. I told you that the youngest supernova in our galaxy is 330 years old. In fact, there was no detection. Since the invention of the telescope, there was no detection of a supernova in our own galaxy, which is a pity. And so the youngest is 330 years old. We expect a supernova in our galaxy every 50 to 100 years old, every 50 to 100 years. So a supernova is long overdue. We're going to find those. And of course, as we find new and new objects, as we discover new classes, we're going to have more questions to answer. As of a decade or 15 years ago, nobody talked about magnetars. Nobody expected to see magnetars. And now they are among the most interesting sources in the sky. There's also a lot of gamma ray sources in our galaxy that do not have any identity. We have no idea what they are. Are they neutron stars? Are they black holes? Are they pulsar wind nebula? Are they active galactic nuclei? Are they star-forming regions? What are they? We need missions which are dedicated to answering the nature of these sources. And last but not least, the origin of cosmic rays. How many of you have heard of cosmic rays? Good. Okay, cosmic rays are actually particles which are coming from space, and they are impinging our Earth's atmosphere. There's a wide range of energies for these cosmic rays, and there's a lot of theories describing where they could be coming from. Supernova remnants are certainly one of the primary sources of cosmic rays. There are observations that support that supernova remnants are the reason for having cosmic rays up to a certain energy. But a lot more work needs to be done to confirm these theories. And a lot of dedicated missions are needed to confirm these theories. Now, there are many, many other questions in other fields that need to be answered. And I'm not the expert on that, but I just picked 3 questions. For those of you who might be interested in studying other things like black holes or do cosmology. So the first question is peaking inside a neutron star. We've been studying neutron stars for 40 years now, but we have no idea what's inside a neutron star, inside that 10 kilometers radius star. We believe it's a sea of neutrons. It's called a neutron star after all. But some theorists suspect it's a sea of quarks, which are the elementary particles which make up the neutron. Some missions will be dedicated to study this question. Probing black holes. Black holes are the least understood objects. We know they exist, but because they suck everything in, it's very hard to study them. So some missions will be actually dedicated to understand how black holes, which are notorious for pulling everything in, they actually can spit out some high-speed jets outward, as illustrated in this figure. So there's a black hole clearly showing jets coming out of it. How can an object which sucks everything in can spit out such high-speed gas? And last but not least, probing dark matter and dark energy. This is, in my opinion and many astronomers' opinion, one of the most puzzling and most interesting questions that's driving astrophysics in the future. As this plot illustrates, actually only 4%, about 4% of our universe is made of atoms. We believe that about 25% is made of what we call dark matter. It's called as such. It's called dark because it does not emit light, but it's been inferred to exist because of its gravitational effect on other objects. And interestingly, there's about 70% of the universe, almost 2/3 of the universe is made of what we call dark energy. That's something that has been introduced a decade ago, okay? And we have no idea really what it is. It's a very mysterious source of energy. It could be thought of as negative gravity, a force that's pulling things outward. And actually, it's been inferred to exist because the universe, the acceleration of the expansion of the universe was found to be accelerating, unlike what astronomers used to believe. So there must be some force which is pulling things outward and opposing gravity. Now, these questions are driving a lot of the missions that have been thought about for Canada's long-range plan, as well as NASA's Beyond Einstein program. So now just to the future, to the current and future missions. I'll start with AstroSat, which is a mission about to be launched, hopefully next year. And that's an Indian mission mainly, but luckily Canada has become a partner thanks to funding from the Canadian Space Agency. And for the first time, Canada will be a partner in a high-energy astrophysics mission, looking at looking at the X-ray sky. But it's a unique mission because also it will have simultaneous optical and ultraviolet coverage. Very soon also we'll have the GLASS, the Gamma Ray Large Area Space Telescope, which as the name indicates, is going to be sensitive to the gamma ray sky. And one of its missions is to identify the gamma ray sources in our galaxy. That's about to be launched very, very soon. In 2011, we expect a mission called the NuSTAR, the Nuclear Spectroscopic Telescope Array, which will have an incredible sensitivity to the hard X-ray, soft gamma ray regime, and it will open a new window to the hard X-ray sky. And around 2017, although that might be very optimistic, Constellation X, which is an approved mission by NASA, and which is one of the missions for the Beyond Einstein program. This is a mission which will combine many telescopes, generating the observing power of just one giant telescope. And it will be answering a lot of questions, ranging from neutron stars to black holes, to galaxy evolution, to Einstein's theory of general relativity, to the nature of dark matter and dark energy, plus many, many more. Of course, I don't have the time to talk about any of these, not to mention that I really don't know much about them. A lot of these are in the planning stage. But I'd like to point out that it's not just high-energy space missions that are being planned. There are a lot of missions at other wavelengths that Canada actually is playing a key role in them. These are like the JWST, the James Webb Space Telescope, which is expected to be launched in 2013. Canada is playing a key role in this mission. And this is an infrared mission. There's also the Square Kilometer Array, which is an array of radio telescopes. Again, Canada is playing a key role in that. And this is a radio mission expected to be operational around 2020. So just to give you an idea about the large number of missions that you, the young generation, will be exposed to once you want to start your career. So finally, I'd like to stop by acknowledging these images and resources, extremely useful. In particular for educators, for high school teachers, this website, the NASA website, is very useful. I'd like also to acknowledge funding by the Natural Science and Engineering Research Council, NASA, Canada Research Chairs, and the University of Manitoba. And I'd like to thank you again for your attention and for staying awake.